Hello, everyone. Welcome to Office Hours, vLLM Office Hours, number 35. My name is Sasha Zelanovic, and I'm the Principal Product Marketing Manager here at Red Hat. I'm joined by Michael Goin, who's been with me for all of the previous 34 sessions. Welcome, Michael. I know you're dialing in from the PyTorch conference. What's going on over there?
Yeah, it's a really fun conference. Yeah, I'm here as a speaker, thankfully, enjoying it a lot. And yeah, I mean, particularly, I've been learning a lot more about how vLLM is used in reinforcement learning libraries, lots of open source libraries. The PyTorch team just announced like TorchForge as well, which is like a really clean library built on top of Torch Titan, which is a great pre-training library. So yeah, it's really just interesting to meet all the different types of people that are using PyTorch and vLLM and interested in where these projects are going. So yeah, definitely meeting a lot of really cool builders as a result.
Did you happen to see any office hours attendees at the conference?
Yeah, definitely. Yeah, someone's from the West Coast. I think like I forget his name, but yeah, definitely some people that recognize us from office hours.
Yeah, that's awesome. That's awesome.
Yeah,
we are actually
they're here today, but maybe they're busy at the conference. I'm kind of
for sure.
away in the corner.
I know it's been busy over there. I've been following from a distance on X, and there's a lot going on. There's a lot of announcements, a lot of exciting stuff. So pretty cool to hear there. We are something similar. We are going to be attending NeurIPS in December as well. We're actually trying to organize a vLLM party at NeurIPS. So if you'll be in San Diego for NeurIPS in a month and a half, early December, definitely be on the lookout for that. We'd love to have you. Anyways, also, how do we forget our main speaker? So Daniele is here, dialing in from Italy. What's going on, Daniele? How are things in Italy?
Hey, it's night. The end of the day for me. Happy to be here.
Yeah, we're really excited to have you. Daniele put a very good presentation on how to build and contribute to vLLM for a meetup in Seoul, one of our bigger meetups, vLLM meetups in Asia Pacific. Extremely well-received session, so we thought it would be a good time to also do this during office hours, especially since we get a lot of questions exactly about how to build and contribute to vLLM. So Daniele is going to share his journey and how he did that, and hopefully entice and encourage people and excite people to do the same. So a lot new in the past few weeks. You'll hear a lot from Michael about InferenceMAX, vLLM TPU, the more and upgraded TPU support for vLLM, a new library that just joined vLLM, compressed-tensors. We did some social about that. You've probably seen it. So Michael will give you a pretty decent update on all of those things, plus the Transformers backend and Deepseek OCR. In terms of office hours, we're excited to have Daniele here to talk about how to build and contribute to vLLM. Next office hours in 2 weeks, we're actually postponing, but we're replacing it with a stream of the Zurich meetup. So Michael and I will be in Zurich doing our first official European vLLM meetup. It will happen, so it's starting at 5:30 p.m. there, so -6, so it's 11:30 a.m. in the morning. So if you're free during the middle of the day, it should be about 2.5 hour event. We'll be talking about intro to vLLM, compression techniques from basic to all the way to advanced. We'll be talking about hybrid models, LMD, Q&A discussion, all the fun stuff. We're streaming the event, so please join us. I'll put something on your calendar once we figure out all the logistics. And then a week later, we're doing a special session, so making up for the miss. And we'll have the semi-analysis guys come over for office hours and talk about InferenceMAX. So you'll hear about InferenceMAX from Michael in a little bit, but we'll do a deep dive into how that came about and what that means for the AI, open source AI community and benchmarking. So pretty excited about that one. And then also on November 20th, a week later, we'll be talking about the vLLM Triton backend. We are recording all these sessions. Link is there. Michael, I'm not sure if you've shared the deck yet. Please do if you haven't. But you can click there and see all of the previous recordings as well as slides. So yeah, excited to have all of you guys here. One last thing that I want to mention, and this is probably a good thing for this topic as well, how to build and contribute to vLLM. I think one of the prerequisites, obviously, is having a GPU. I'm sure Daniele is probably going to say something along those lines. But so our friends at AMD, and I mentioned this last time, have offered all of the office hours attendees 100 free GPU hours. There is a form. I'll actually, let me put that form in chat right now. There's a form that you can submit to request those 100 free GPU hours. Here is the form coming through chat right now. So click at request 100 hours. You get access to state-of-the-art free AMD GPUs. If you need more, if you want, what they told me is if you want 1,000 hours, if you want a box of 8 for building vLLM on top of AMD, that's also possible. So what you can do is, request the free 100 hours through the form that I just sent, and then Slack me in the vLLM Slack. It's also linked right there. I just find my name, Sasha Zelenovic, SASA, and I'll connect you with the right people at AMD who can turn those 100 into 1,000 or even more. So pretty exciting, and we want to thank AMD for offering this for the Office Hours attendees. Anyways, with that, Michael, I'm going to pass it over to you.
Thanks, Sasha. Hey, everyone. Good to see you again. And for ones that are new here, let's briefly go over what is vLLM if you aren't familiar with it. At this point, it's the fastest growing de facto standard for open source model serving, Apache 2.0 license, supporting over 100 arches. I think actually now over 200 different model architectures, and of course getting making it easy and more importantly fast to deploy all the various open source large language models that you're interested in on, of course, NVIDIA GPUs, but also through the power of software abstractions, working on a wide variety of hardware providers that work and develop their own hardware backends, which Daniele will cover some of the complexities and how we take care and build for these different backends like AMD, Intel, Google, AWS, Huawei Ascend, even like Meta X, Rebellions, many different hardware plugin architectures supporting vLLM. I will briefly cover some exciting milestones we've reached in popularity with star milestones. But yeah, it's a very active flywheel of an open source project with a ton of contributors from across industry and research. Yeah, it's just a really exciting place to be working on in a shared community, and hope you're already a part of it or looking to join in on the fun. So I'm going to cover, as Sasha mentioned, some new things that that vLLM has been involved with over the past 2 weeks since the last office hours. One thing that I was really excited about and a part of was SemiAnalysis' big InferenceMaX article and website and sort of open source benchmarking release. This was a really cool effort from the SemiAnalysis team to they sort of did ClusterMax, which is trying to give grades to all the different hyperscalers and also the GPU neoclouds for how reliable are their systems, how high quality is their hardware, what are their prices, where is their security, and generally just trying to scope them out for are they ready for enterprises to make big deals with them. And similarly for InferenceMaX, the goal is to take what available state-of-the-art open source software is out there like vLLM and apply it on the bleeding edge hardware, the latest like Blackwell GPUs from NVIDIA, the latest MI355X GPUs from AMD, and apply those to the common state-of-the-art models of the day, running them across standard workloads. This is an effort to see basically, is the software out there ready to take advantage of the latest hardware, or does the software still need time to bake? And you can see we're running like vLLM and even comparing against Tensor TLM on a variety of Hopper, Blackwell, and AMD GPUs across generations too. And yeah, we're like able to see very clear 3x up to 4x bumps from H200 to B200 on NVIDIA, and AMD as well, scaling well across their generations from MI300X up to MI355X, and showing that the open source software that's out there in vLLM is able to really take advantage of the hardware improvements and fully utilize the fresh new hardware that you're spending a a lot of budget on. So you really want to make sure it's utilized well. So I recommend you to check out our article, which covers a lot of the optimization work that we did with NVIDIA in order to make particularly Blackwell very well supported, and integrating a lot of kernels from their various open source libraries into vLLM. And read the semi-analysis article themselves, where they compare and sort of analyze these very dense graphs and break apart what it means for one hardware to be compared to another. And they also go into total cost of ownership, TCO analysis for how much it costs to host and own MI355X versus like a B200. And so it's not all just about raw performance. It's also about what's the cost to own it, not just the price you pay, but also the racks and the power and all those various things. And I just want to shout out that, as I mentioned, they did include, some numbers comparing vLLM against TensorRT-LLM, which is NVIDIA's, custom inference engine. Naturally, people have a perception that TensorRT-LLM is like always going to be better than vLLM, but we're really happy to see that vLLM these days is easily, trading blows with TensorRT-LLM on, state-of-the-art models like GPT-OSS on both H200 and B200. A great validation for the work we're doing in the project, the collaboration we're doing with NVIDIA to make sure that vLLM, matches up to even their, custom best effort in their own engines. As I mentioned, if you're interested in this stuff and benchmarking and analysis, highly recommend checking it out. It's a cool project. And as Sasha mentioned, we'll be hosting them in 3 weeks with a special topic. They will present their methodologies and how they built this project. Next, I want to cover an exciting release from last week. We've been working and helping out the Google TPU team on their next generation TPU backend in vLLM. If you remember, there was kind of a previous release for vLLM TPU earlier in the year. I think in like May at Google Cloud Next. And since then, they've sort of retooled and refactored a lot of things and changed the approach in order to better identify bottlenecks for large-scale inference as they really scale out their usage and deployment of vLLM with customers and the community of users. And they're finally ready to release this, powered by the new TorchAX backend, which now allows for model definitions to be still written in vLLM using PyTorch, but using TorchAX to essentially transpile Torch operations directly into JAX operations, and then using the traditional like JAX compiler stack to compile for TPUs like Google does internally, and like many of the raw TPU users do on TPU. And then also this allows them to write custom JAX implementations of models for like the very best performance when they're working with their customers. So it's actually like a very cool idea, and sort of maybe a new paradigm for mixing like PyTorch and JAX together that many companies that sort of straddle between them struggle with, as they're very different machine learning frameworks. This may go to be useful even beyond TPUs and be useful for GPUs that want to run on JAX. But yeah, we're really excited to be working closely with the Google TPU team to help foster these experiments and ultimately push inference performance on TPUs as well, so it's easier for people that just want like cheap hardware deployments available, no matter what hardware is available, just to have the same easy to use interface within vLLM. So recommend checking out this announcement and what's been new over the past several months. And obviously there's performance improvements included in there. Another shout out I want to give is something that actually was a project we started at Neural Magic 2 years ago or so, before we were acquired and joined within the Red Hat team. We've finally graduated compressed tensors to the vLLM project as a whole. So now the whole LM compressor, compressed tensors to vLLM stack for producing compressed or quantized models and representing those compressed models in an open format that can be compatible with not only vLLM, but also Hugging Face transformers and native PyTorch frameworks, and like other compression libraries like Torch.io. This sort of open format can now live properly where it belongs in the vLLM project, so that many other open source projects feel more comfortable about working with it and expanding with that. And as a result, we're working with several other teams at companies and open source projects that are looking to produce their own compressed checkpoints and represent them in the compressed tensors format, so they can work with a variety of libraries that implement the format. So yeah, just an FYI. Recommend you check out the format, but if you're just interested in compressing and making quantized models, FP8 checkpoints, FP4 checkpoints, still just check out LM compressor and use that to produce the models. Hopefully, as a user, you don't need to know compressed tensors exist. It's just easier for people to use it that way. Next, I want to cover like a key feature. Hopefully, if you've been following vLLM for a while, you've been hearing about the Hugging Face transformers backend, using model definitions defined through transformers rather than having our own model definitions in vLLM. This has been a great boon for supporting many of the model architectures that aren't state of the art, but still, regardless of that, have users or specific use cases. And Harry from the Hugging Face team has been expanding this over the weeks and months, and most recently, MOE models are added to the list, and they're hoping to expand that out. So we obviously still support Qwen 3 in vLLM natively, but now you can run it using the transformers backend, and hopefully we can make it more robust and scalable with the different types of parallelism and performance features that we're developing in vLLM. Next, I want to cover an exciting release that you've hopefully heard about in the community. Deepseek released their latest model, Deepseek OCR, which is a very small and efficient vision language model from them. And it covers. I highly recommend reading the paper and analysis. There's been a lot of interesting things of, they really went for token efficiency and in the vision tokens of, the model. And even showing claims that if you tokenize like pictures of text, you can actually represent that in less tokens than if you tokenize text directly. So this is maybe thought of as an idea for achieving really long context. Maybe if you render the text in an image and then feed those pixels into the model, and somehow that's more efficient than just a straight text tokenizer. Lots of people are speculating and writing about this. I'm a little skeptical of myself, but certainly the results they show in the paper are really cool, and it's certainly a cool thing to think about in the future as we go to really long context. What's the best way to store and provide, text, image, audio over long contexts to model and try to compress them in some way that's different than just relying on like Unicode tokenizers, which certainly don't seem that great. So obviously we were like a launch partner with this model, and it's landed upstream in vLLM already. So it's a very efficient model. So if you have any tasks that require OCR or just general vision language modeling, recommend giving it a try. It's a surprisingly efficient model, and has very high quality for, I think, enterprise useful tasks. Lastly, I want to give a shout out. As I mentioned, vLLM reached a big milestone over the past week. We've just the project itself has reached 60,000 GitHub stars, and we're just so thankful for the vLLM community for growing so much with us. Of course, the users and enjoyers of vLLM, but the many contributors. We have over 1,700 unique people that have landed code in the project, which is pretty amazing for a project that's only been around for like 2 years, basically. And of course, we're very thankful for the adopters in industry, in the hardware companies, the model vendors, and of course, academic institutions and individual hobbyists and users. We all come together to use these things. Yeah, thank you very much for being a part of the community. And with that, I will end my spiel and hand it off to our talented speaker, who's going to cover a lot of the fundamentals of how vLLM is built and works and how you can contribute. So Daniele, take it away.
Thanks, Michael. So I'll be sharing my screen now. All right, let's see if this actually works. All right, so my presentation is actually hosted on GitHub. So I just posted the link in the chat. This is the website for the talk if you want to follow along. So my name is Daniele Trifirò. That's my GitHub. A little bit about myself. My background is in physics, actually astrophysics. I spent some time doing research in the gravitational wave field. Now I'm a senior software engineer at Red Hat in the AI inference server team, working remotely from Pisa, Italy. You might know the city for the famous Leaning Tower. And so let's talk about what I do. So I like Python. I like free and open source software. I've been at Red Hat for around a couple of years. I started working on OpenShift AI model serving, so everything that to do with serving ML and AI workloads. And I eventually started focusing on vLLM, and now that's basically all I focus on. So what I built as part of Red Hat AI Inference Server is basically a tested and verified build of vLLM. So my duties, of course, involves building vLLM, testing vLLM, a lot of release engineering, and which obviously leads to contributing to vLLM and its ecosystem. So if you want to know more about the Red Hat AI Inference Server, you can go to this address, and there's a pretty comprehensive blog post. So let's say, how do I get started with vLLM? Well, it's easy. It's open source. You can clone the repo, change your working directory, and you can get to work. A few suggestions. So the docs website is very, very useful. There's a lot of different resources related to contributing to the project, not only actually using the project, but contributing as well. It's very useful. Another important thing is the issue tracker. Most of the time, if you have some kind of issue, some kind of problem, just searching here will yield a lot of useful information about the issue that you're encountering. Perhaps someone has already encountered it, or maybe someone else has already solved it. So yeah, that's important. And well, having access to some kind of accelerator, so a GPU or some other kind of accelerator, does help when when developing. So let's lay down some vLLM facts. So the current vLLM version is 0.11.0. It was released October 10th. 0.11.1 is brewing, so the RC1 is already available. Usually there's a release around once every 3 weeks, and as Michael mentioned earlier, there are more than 1,700 contributors as of today, and just 207 in the last release. So there's 65 new contributors. This is a 200 contributor increase since just a couple months ago, just to give you a sense of the scale of the rate at which new contributors are contributing to the project. Of course, this means that a lot of code is being pushed out for each release. Just as an example, for the last release, the difference between v0.11 and the previous release is more than 1,000 files changed, with 74,000 insertions and 62,000 deletions. This is basically a 13,000 line net difference in just a few weeks. So this is a lot of code. This is basically what the vLLM repo looks like. It's a lot of Python. That's 374,000 lines of Python, a lot of JSON, a lot of CUDA, a lot of Markdown, but almost 60,000 lines of C++ and CUDA. So there's a lot of stuff here. So let's get started. Let's talk about how to build it. So this is it. It's easy. You clone it, you create a virtual environment, and you install the build requirements. You set the target device, and you build it. So you have your wheel, and you're set. You can install it. Well, you can also build it with other tools. The kind of setup.py approach is somehow deprecated. You can use the build module, or you can use UV if you like that. I do. But this is not all of the story, right? There's a lot of complexity hidden behind all of this. So what's not simple out of this? So there are several targets. So there's NVIDIA, there's AMD, there's Google, there's Intel, there's CPU builds, and more and more, like different architectures and so on. This, of course, leads to having different tool chains required depending on the target. Of course, for example, you need the CUDA toolkit with the NVIDIA compiler. You might need the AMD toolkit with the HIP compiler, and so on. Again, you also need a lot of hardware in some cases. Like the build can be very hungry for memory and CPU, like several gigabytes of memory can be required per process when building. So yeah, this is just a brief overview of what are some of the challenges that we encountered. But let's take a small step back and let's talk about what is vLLM. It's just a Python module with an extension. So what is this? This is it. This is basically a very simplified view of what a Python module with an extension is. It's the setup.py that actually powers the build of the package. So you just you just import the setup function. You set the name of your module, and you define the actual sources and the kind of rule that you need to build your sources. Basically, the main point is this. You define the name of the extension and the source file for the extension, and you build it. So, of course, this is just a very simplified example. It's not working, but you can find a real working example of a very simple Python C extension on my GitHub. So let's talk about the vLLM extension. So first of all, vLLM is built on top of Torch. So it means that when compiling this C and CUDA pieces of code, you always are linking against PyTorch. So the custom rules that we use to build these extensions are done using CMake and Ninja, and depending on the kind of accelerator that we're building for, you might have different compilers, as I mentioned before. So for CUDA, it's NVCC, NVIDIA compiler. For ROCm, it's a combination of hipified Torch to kind of convert the CUDA sources to HIP, and then you compile them using the HIP compiler. And again, for other targets, it depends. So let's talk about configuring the build. So there's a few environment variables that are always required for basically all the targets. So for example, the target device, the accelerator. So you can set vLLM target device to CUDA or ROCm, but you also have other targets such as CPU, TPU, XPU, and so on. One other important environment variable is max jobs. This is pretty important because it kind of sets the parallelism of the build. And since each job will require around 4 gigabytes of memory for the CUDA build and 1 gigabyte of memory for the ROCm build, you can see that you cannot parallelize this too much, because otherwise you will end up going out of memory and crashing your machine. So this is quite important where you're actually starting to try and build vLLM locally, because this will crash your machine if not configured properly. Another important environment variable related to parallelism is MVCC threads. This is, of course, CUDA specific. Basically sets the number of threads to use per job when building for multiple architectures. And I'll talk about what architectures are. The architectures are kind of this kind of list of numbers which corresponds to specific models of NVIDIA GPUs, or in the case of ROCm, PyTorch ROCm Arch. So, for example, the 7.5 architecture corresponds to an NVIDIA Tesla T4. The 8.0 corresponds to an NVIDIA A100 card, and so on. The same for ROCm. Of course, using more architectures increases the compilation time. I won't go too much into the details for all these architectures, environment variables, but these are a few useful references, such as the NVIDIA GPU and capability mapping. So it maps the capability number to the actual GPU models. You have the same thing here for Torch. It's basically a pre-built mapping that is in the Torch source code. And then you also have the same thing for ROCm. So going forward, one of the important things that I mentioned earlier is that Torch, these Python extensions link against Torch. And since many targets have their own Torch flavor, for example, ROCm CPU has its own custom Torch flavor. Google TPU has a custom Torch implementation. Same for Intel, same for Neuron, and so on. You have to make sure that you're using the correct version before you start building. So, for example, one way to do it with pip is to set the pip as extra index URL, and in this case, we're pointing it to the download pytorch.org will CPU index. Or if you like UV, like me, you can set UV torch backend to automatically point to the right version. So let's go forward and talk about local development. So what can you do to get started? As I mentioned, you can start installing the build requirements in a virtual environment, and then you can just start installing the package with the no build isolation flag, because we already installed the requirements, and I might talk about this later. And this is just the editable flag to be able to edit Python code and immediately test your changes without having to reinstall. A few other useful things is that if you're only editing Python code, I recommend using vLLM use precompiled, which basically will automatically fetch the latest available precompiled will from the upstream vLLM distributions, and use that instead of rebuilding it from scratch, which will make the build very, very fast compared to the standard full build. You can also do the same thing with the latest precompiled nightly wheels by setting this other environment variable. So you'll need both of these two, and this will go much, much faster than building from scratch. And sometimes it's easy. The kind of change that you're attempting to do doesn't really involve the usage of a GPU, for example, and you might want to test it locally without spinning up a GPU instance or whatever. So you can set the target device to CPU and setting the Torch backend to CPU, and this will build vLLM from scratch in just less than 30 seconds, and it's good enough for some purposes, like, oh, I just want to test out some change in the OpenAI API. you can run it locally with a very small model and you can test it out. This is also very useful to do some kind of integration testing in CI. All right. So give you a few more extra tricks. So for example, you can install a nightly for a specific upstream commit. So you can check out the reference, get the vLLM commit, and then install using extra index URL to install the vLLM version coming from this specific index. So basically, you will get the pre-built vLLM version from that specific commit. And similarly to this, you can actually install vLLM using the precompiled approach by first downloading a wheel from a specific commit. So basically, again, you decide what vLLM commit you're trying to use. In this case, I'm using the previous commit with respect to the Git head. I'm using pip download to download the wheel without downloading dependencies and so on. So I get this wheel file. And then again, I use vLLM use precompiled, and you set the precompiled wheel location environment variable, which basically will mean that the precompiled artifacts are going to be extracted from this wheel and installed. Again, this makes the build very fast, and you can make sure that the wheel that you're installing actually matches your kind of development branch base. All right. So anyway, if you're interested in this kind of stuff, there's a lot of useful information regarding this kind of installs with the wheels.vllm.ai index, and it's all in the docs. So please go check it out if you're interested. But this kind of workflows are mostly related to developing only when you're only developing codes in Python, right? Sometimes you actually do need to compile the kind of CUDA kernels that make vLLM fast. And so the way to speed this up is to use a compiler cache, such as Ccache or SCcache. So basically, what these programs do is they intercept the compiler invocations by the build system and try to see if it has already been built, and if so, just give you the cached artifact so that you don't have to build the same stuff twice. This is especially important if you don't want to rebuild everything from scratch every single time. The cool thing is that vLLM's build system will automatically use this if they are available, so you don't have to rebuild everything every single time. So there's a few caveats to this. So if you're using pip build isolation, so like pip install the current directory, for example, or pip install to a specific path or whatever, this uses temporary build directories, which might cause cache misses. So I opened just recently a PR trying to improve this behavior, which should be merged soon, hopefully. But in the meantime, you can use these approaches with setup.py, building the wheel in an unisolated environment, or just setting up the develop kind of workflow. These are deprecated, so I don't recommend using them too much, but in case you're desperate, it always works out. So a few more suggestions to keep the build fast. So only build for the targets you need. So if you're developing vLLM explicitly for NVIDIA A100, just set the CUDA arch list to 8.0, which corresponds to A100. And if, for example, if you're building for ROCm, just build for the GFX 942, because each target that you add to this list will make the build much, much slower. It basically increases almost linearly with the number of architectures that you add. As I mentioned before, sometimes just building the CPU version might be enough for your purposes. So you can set the target device, and you can do builds really, really quickly, and you can also test locally without having to use a GPU. Of course, this doesn't work if you actually need to work with CUDA code or with large models or something that doesn't fit in your CPU. So these are some other tricks. So for example, if you need to install a specific reference, a specific Git ref, you can do something like this. Basically, force the Torch backend to GPU, force UV not to install binaries for a specific package, and then you can actually install from a Git reference, for example. In this case, v0.11.1 RC1. This is especially useful, the kind of no binary approach, when you're developing plugins. So you can set something like vLLM target device empty, and then you tell it to install vLLM without using binaries. So this will attempt to rebuild vLLM from scratch, but when you set something like vLLM target device empty, you're not actually doing the build, and this is especially useful for hardware plugins. Yeah, so what are plugins? So basically, the maintainers realized that it was kind of hard to add support for new accelerators. It's mostly due to the fact that you have to modify files in trees. There's a lot that the code base moves really fast, and it's sometimes really hard to keep up. So this kind of vLLM plugin system was developed. There's a blog post here if you want to read more about it. The goal was to make vLLM device agnostic, so that you could easily add new devices. And the gist of it is that you can implement support for new hardware via an out-of-tree plugin, which automatically registers with vLLM. So there's quite a few implementations currently. So there's IBM Spire, AWS Neuron, Intel Gaudi, Huawei Ascend, Rebellions as their own NPU, MetaX as their own GPUs, and they all have their own plugins. Some lives under the vLLM project umbrella, some not yet. But yeah, there's a lot of activity in this regard. So how does this work? Well, it's basically quite easy. From vLLM, you actually import this platform class. You register it this way. You set your device, the type of your device, and then you implement all the relevant methods, which I won't cover here. And then in the setup.py, you just define the entry points to register your module. If you want more details about this, there's a whole documentation page for it. So it's a good place to start reading. So I did not cover a lot of stuff here. Basically, what I want to stress about is that vLLM has dependencies, which are also Python extensions that link against Torch. So as an example, Flash Attention, Flash Infer, Flash MLA, Xformers, all of these build against Torch. So depending on what you're doing, you have to make sure that Torch version matches and that the Torch version supports the architectures that you're building for. So you have to be careful about this. Some dependencies instead heavily rely on just-in-time compilation, such as DeepGem, for example, requiring MVCC to be available. Stuff like this you need to keep in mind. Like, it's not enough sometimes to just build vLLM and ship it. So again, as I mentioned, the Torch version has to match, the CUDA version has to match, and keep in mind that not all of architecture supports all features. So for example, you might not have quantization available for certain architectures or some specific types of quantization, or you might just not have a model work for a specific architecture. Okay, so let's move over to Docker, I guess. So why? So the vLLM wheel in CI is built basically as a Docker file step, and there are Docker files for for each target. So there's Docker file, which is for CUDA, CPU, Nightly Torch, which is basically the same as the CUDA Docker file with using the Nightly Torch version. There's a PPC build, ROCm build, S390X build, TPU, XPU. So each one of these builds vLLM with setting up the environment and the toolchain with their own set of rules, which is actually a good way to learn how this actually works, because you can just go into the Docker file and see what kind of environment you need to actually build it from scratch, which is very useful. I will focus a bit about the CUDA build. So it should be simple, except that the Docker file is not exactly a small Docker file. It's 543 lines, so it's not exactly simple. So what to do here? Well, there's a guide which helps you generate a graph from this Docker file, and this is actually part of the documentation, which can help you kind of unwrap the way that a Docker file graph is built. So this is what it looks like. It's not exactly, it doesn't look simple, but it actually is. So it's a base image usually that sets up the toolchain. So it sets up CUDA, MVCC, the environment variables, and the Python build and runtime dependencies. This is what I'm talking about. It starts from a CUDA 12.9 image from NVIDIA. Then there's the actual build step, which basically builds the vLLM wheel with a few extra configurations, such as SC cache and so on. And then you have the vLLM base stage that depends on the previous build stage, because it actually installs the vLLM wheel. And then you have the final stages, which are the vLLM OpenAI stages, which basically contain all the extra dependencies needed for the OpenAI REST API to work correctly. And then last but not least, there's a test stage, which is what is being used by CI to run tests and whatnot. So these images are built with BuildKite, and as I mentioned, the tests are run in the test stage. So that's where you have to start if you want to debug this locally. Now, CI can be a bit flaky, so it can be tricky to try and understand if your PR is failing because you screwed up, or is failing because some tests or something is flaky. So I recommend looking at the CI runs on BuildKite, comparing against main or the other runs, and eventually wait for maintainers to retrigger CI in case it's some kind of transient that made your build fail. You can filter on BuildKite by branch, basically select your branch or select main, or see how other builds are doing, just to get a sense of how this is all going. And I'll just leave here a bunch of useful links on CI. So there's the first one is about the fast check, which is the fast check for all PRs that is run just to make sure that just a general sanity check, I guess. Then the full CI is here, and there's also an interesting repository, which is the CI infra, which kind of defines how some of this stuff is done. And there's also the BuildKite docs. So these images are built and released. There's the Docker Hub vLLM OpenAI image. There's the ROCm vLLM image. There's the vLLM TPU, and some nightlies are actually available on Docker Hub. CI actually uses a different registry, which is this public ECR AWS, which is kind of a sad name, but it can be useful to pull a specific image, a specific nightly image. So you want to pull an image from one of the latest commits, you can just check out main, check out the commit that you're interested in, get the ref and just do something like this to possibly get the image. Sometimes the reference you're interested in might not be available, so I recommend doing something like this with Scopio to list the available tags. So here comes a little bit of advertising. I guess that as part of my job, we maintain some Red Hat midstream builds. So what are these? These are just images that are based on the Red Hat Universal Base Image, or UBI. It's kind of a RHEL image that is to be used as a base for lightweight container images. You can think of these images, our midstream images, are kind of a staging area for RISE. And these are available on the Quay.io registry. So you can find them at these locations. And something that's going to be coming up soon is the TPU build. All right. So let's talk about testing. So usually when you have a Python module, you kind of say, okay, let's use PyTest, right? So you can just run PyTest and start testing, right? Well, this is an example of what happens when you just want to list the tests in the vLLM repository. So it takes like more than 1.5 minutes just to get a list of the tests, and you get almost 50,000 tests. So this can be overwhelming, right? How do you deal with this? Well, I'll give you a few tips here as well. So since BuildKite is used, you can actually check the pipeline definition and see which tests are run and how. And of course, you just go into the repository, you go into the .buildkite directory, you go into test pipeline, and you see a list of entries that look like this. So you have a label, which is basically what you see in the BuildKite web UI. These are just basically timeouts and other configuration options which you must not care about. But what's important is the source file dependencies and the commands that are going to be used. And here is the important thing. Basically, run PyTest verbosely. You capture the output, so you actually get the output from PyTest, so from vLLM, and then you run all the tests in this directory. So if you're interested in knowing what tests are run and how, you just go look into this file, and you can figure out what you might want to run. Another trick is to use PyTest-K to select tests by name and or pattern. So for example, you can provide part of the test name to just select that test, and providing a specific directory or a test module also helps, because as I showed earlier, even test collection is very, very slow. So it's kind of annoying to wait like 1.5 minutes just to find what tests are available. I'll give you some more advertisement. This is a shameless plug. This is one of my personal projects. It's basically a PyTest plugin that allows you to select tests using Fuzzy Finder. This is kind of interesting because it allows you to see a preview for the tests. You can select one test or multiple tests and just run it. You can find it at my GitHub, and you can also get some other information about Fuzzy Finder. Anyway, what else can we do? Well, there's functional tests, there's benchmarks, and that's one of the most important things. Like, we strive to be fast. vLLM aims to be the fastest inference engine there is, right? So regarding functional testing, one way is doing evaluations. Like, how can we make sure that vLLM behaves as we want on a given model, right? So the solution is LM evaluation harness. Basically, the idea is to evaluate a given model on a set of tasks, on a task or a set of tasks, and kind of get a score out of it, and make sure that it it scores a certain amount. This is especially important if you're running quantized models, so you want to see how much performance the model loses after quantization. And the tasks that this is evaluated on is can be one of these task groups or a specific task. There's a lot of them. Just as an example to make clear what's a task group. A task group can be the OpenLLM leaderboard. So you have a bunch of different tests. Some might be multiple answers questions or something different. You run all of these evaluations and you get the results. So you have a few options here. For example, you can use the vLLM backend in an LM evaluation harness, which sometimes is enough just to get some simple answers, but most of the time you will end up having to test your own vLLM version that you built or that you have installed locally. So you can spin up vLLM manually and use local completions. So for example, in this case, you build a configuration file. It's just a JSON file with a model, the base URL onto which vLLM will be listening on. In this case, I'm assuming it's running on localhost on port 8000. A few extra configurations regarding how the endpoint is going to be hit, and then you just run LM-eval. In both cases, you just wait a long time for all the evaluations to complete. Anyway, yeah, so the last step is, of course, comparing your results with the model card. So in this case, we're talking about a quantized model. So we might want to go look at our results and compare these against the model card, which you can find on Hugging Face. So this was about accuracy, but let's also talk about performance. So Neural Magic developed this GUIDEL plugin, which was eventually merged into the vLLM project. It's basically a framework that allows you to run a lot of different kind of benchmarks on vLLM. It's quite easy to get started with this. So for example, you start vLLM, you install GUIDEL, possibly in another virtual environment, and then you start the benchmark. Basically set the targets, set a few other options for the for GUIDEL. The important thing is this: the rate type specify the kind of test that you want to run. So in this case, we're trying to run a kind of throughput kind of workflow to see how many tokens per second can vLLM actually push out. And so there's a bunch of useful flags that you can use. So data, specify the data set to use, this, or for example, synthetic data to be generated. You can set the maximum duration in seconds for each benchmark to run. You can set the rate type. Again, the kind of benchmark to run. The default is sweep, but you can also have synchronous request, throughput benchmark, concurrent request benchmark, constant Poisson, and so on. So anyway, you get all of these details for on how to configure GUIDEL at the GitHub repository. So I'll show a quick demo just because I think it's pretty cool. So again, it's showing you everything that I've shown you so far, installing GUIDEL. Check out the version. So this might be 030 dev, and then you just start it. So first of all, it creates the synthetic requests, and then it actually hits it, and you get a live terminal UI that shows you how vLLM is doing in terms of tokens per second, latency, and everything that you might need. And in the end, the results are pushed to a JSON file for further analysis. All right. So let's talk about contributing to vLLM, because we talked a lot about building and setting up environments, but this is not all of it. There's also the part about contributing to a project as large as this. So the first thing is you have to sign off commits with git commit -- sign off, since the developer certificate of origin sign off is one of the required checks. So you will always need to have this, otherwise your your basically CI checks will fail and your PR will not be merged. The second thing is actually running pre-commit. Basically, it's a standard tool to use to enforce some coding standards such as formatting, linting, so on. This is quite easy to set up locally, so that you don't have to wait for CI to say, oh, you forgot a comma somewhere. So it's easy. You just pip install pre-commit. You install the pre-commit hook so that when you run git commit, the checks are actually run. Or you can also run it manually, like this: pre-commit run all files. Or you can run it on a subset of commits. So, for example, to run it on the previous 10 commits, you can do something like this. Or if sometimes you just want to commit but don't want to wait for all the pre-commit verifications to succeed, you can just do git commit no verify to skip the pre-commit verification. Don't use this if you're actually expecting your PR to be merged, because all checks must pass for something to be merged. So you can do that as a development step, but not for the final result. So some other things that you should be doing when contributing: so write tests like unit or integration tests, add documentation to docs if it's something that needs to be documented, and if possible, try to keep changes small and incremental, possibly atomic, so that each commit actually makes sense and is understandable by reviewers, if possible. And yeah, there's also another important thing, which is the PR titles and classification. So there's a bunch of kind of tags that are used to classify the PRs into different categories, such as bug fixes, CI and build improvements or fixes, documentation builds, model just for adding new models or improving existing ones, front-end changes to vLLM front-end, kernel changes, core changes, and so on. So there's a lot of different classes. You can see some explanation on each one of these on the docs. Again, I highly recommend checking this out. So one other thing is that there's a lot of issues that are labeled as good first issues. So if you want to spend some time like getting to know vLLM, try to look for these good first issues, and then you can start actually looking at the code and starting to contribute. Another important thing is join the Slack, our Slack workspace. So slack.vllm.ai, you will get an invite and you can actually talk. There's a few really useful channels, such as the questions channel, documentation channels, contributors channels, but also PR reviews, like if you actually want to get some feedback on your reviews and you want to start a discussion somewhere else. There's also a lot of special interest group channels, which usually start with SIG, and I also recommend to check those ones out. And I guess that's it. Thank you.
Yeah, great coverage. Very thorough. I think a lot of people found that useful just from looking how many people are watching the live stream as well. So yeah, thanks a lot. Obviously, we're a bit over time, but if anyone has pressing questions, feel free to ask or come off mute. Okay, well, we'll call it there for now, since we're over time. But thanks, Daniele, a ton for doing this great presentation, and of course, yeah, helping a lot with the quality of CI and build in upstream vLLM. Yeah, really appreciate it. So take care, everyone, and see you in the coming weeks. Have a good week.
Thank you. Bye, everybody.